big honor to have Michele with us today, and it's pretty fitting that I introduce him. He's going to be my new boss from this fall, and he was my boss back when I was doing my master's thesis with Andrea Hulzer, and we had a paper together. And, it was a great pleasure working with him, so I hope it's going to be a pleasure to hear him talk today about, what is it titled? Non-minimal terms in Goldstone Boson theories.
Okay, so thank you very much. It's a great pleasure to be here. And so I'm going to talk about theories with Goldstone bosons and the most general parametrization of this type of theories that has a wide variety of applications in particle physics that I will describe some of them. And so this is based mostly on this last paper, which I put with L9 in Florence. And these are other papers that related to this subject. In particular, this is the first one that I happened to do with Diego. It was part of his diploma thesis. And it's the paper that started my interest in this field. And it's funny that 5 years later you keep working on the same things. I didn't expect this at the time. So please feel free to ask me questions. I try to make this not technical, and I understand that here there is very different interests, so please stop me if things are not clear. So so this is my outline. So a lot of progress in the understanding of strong decoupled theories has been done using ADS-CFT and generalization, so effective field theories in full dimension. So we'll briefly review this type of descriptions and what they are relevant for the relevance for particle physics. And then I will move to generalization that really go beyond the idea of extra dimensions that you have here or in other generalization that people consider. And as I will show, this generalization really have different features that are not captured by the effective descriptions based on extra dimensions. And I will apply these ideas to two examples that are relevant for particle physics. One is the idea of the Higgs as a Goldstone boson, and the other is low-energy QCD, which at the technical level they are very closely related. So I think I don't have to convince many people that strong dynamics is still a frontier of particle physics. So it has, it happens in a wide variety of physical system, and the one that I will be interested in is composite Higgs models and low-energy QCD. Now, in this field, there has been a lot of progress in the last almost 20 years now. That is typically done in the Lagrangian limit. And especially when the theory is conformal, and I didn't mention it here, but also, of course, in supersymmetric theories. Now, this is very nice and has been very useful to understand the features of strong coupling, but it is very important to keep in mind that it is not in general applicable to the physical systems that you are interested in, and in particular these two, it might be questionable whether you can apply this type of tools. So the the chief example of progress in Lagrangian theories is the ADS-CFT duality that relates a strongly coupled conformal field theory in 4 dimensions to a weakly coupled gravity theory in 5 dimensions. And this is an exact duality, in particular if you consider n equal to 4 Spreng-Mills or also generalization. And so there is a mapping for any question that you can ask in the strong coupled conformal field theory side that can be answered with a weakly coupled computation in the gravity theory. And in particular, there is each operator of the 5-dimensional of the conformal field theory becomes geometrical in the 5-dimensional theory and is associated to a field of the 5th dimension. Now this is really a duality, so it's kind of essentially a mathematical statement at this point. But this type of features, they go even beyond ADS-CFT, and they are associated to the Lagrangian limit. So if you think of QCT Lagrangian, there is the important result that, for example, that the theory is a weakly coupled theory of mesons. So this means that, for example, the trilinear vertex GT3 mesons goes to 1 over root square of n. And so this theory ought to have a weakly coupled description in the Lagrangian limit. Now, this weakly coupled description is, in fact, can be parameterized in general by means of five-dimensional gauge theories. And the way it goes is the following. So it happens in ADS-CFT, but it is more general than that. So if you take a gauge theory in 5 dimension, for example, with an arbitrary metric, you have that the theory is not normalizable, and so has a dimensional full coupling, which is G5. And so when G5 is small, the theory is weakly coupled, and so the resonances of the theory that you obtain from a Kaluza-Klein reduction, they have the properties of the resonances in a Lagrangian theory. So this gives the idea to describe more in general than conformal field theory, a strongly coupled Lagrangian theory by means of an extra dimension, for example, with the gauge theory. And in particular, the inverse of the gauge coupling, measured relative to the IR scale of the theory, is essentially plays the role of n, of the number of degrees of freedom. So this geometrical picture that you have in ADS-CFT, it works also if you have ADS geometries, and there is a very nice way to realize symmetries by means of extra dimensions. So, for example, suppose that you have a global symmetry G. So this global symmetry G becomes a gauge symmetry in 5 dimensions. So you will have a gauge theory with group G. And for example, by imposing a boundary condition on the IR brane, you will be able to parameterize spontaneous symmetry breaking in this theory. So suppose that the group G is a spontaneous broken to H. This can be realized by imposing Norman or Dirichlet boundary condition on the gauge field in the IR theory. So in this way, you will realize the physics of Goldstone bosons that emerge every time that you have a spontaneous breaking of a global symmetry G to a subgroup, that they become a geometrical quantity. They are the Wilson line of the gauge field across the extra dimension. So in this way, you will get the low energy dynamics of Goldstone bosons, which is universal. So it doesn't depend on extra dimension, but it will also describe the tower of resonances, which are other excitation of the theory, and with couplings to Goldstone bosons, for example, that have some memory of this geometrical picture. So now I would like to describe the type of systems where you will that this type of tools can be applied, and so let me start with the idea of the composite Higgs. So now that we have that the Higgs has been found, it's still so a very compelling scenario is the one that where the Higgs is a bound state of some strong dynamics. So the idea is a bit like the old Technicolor theories. So you have some strong sector that we confine, and it produces resonances. And differently from old Technicolor, among these resonances there is also some bound state which has the quantum numbers of the Higgs. So these theories are motivated by the hierarchy problem, because in these theories you have that you will have a composite scale, also a dynamical scale of the theory, And this scale will act as a cutoff on the quadratic divergences of the Higgs mass. So, for example, the gauge loops, the standard model loops, they will be cut off by the scale of the first resonances. Another way to say this is that in this theory the full Higgs doublet is a composite state, so has a finite length which is of the order of the inverse dynamical scale, and so the theory cannot probe distances shorter than this fundamental length of the theory.
So sorry, but I mean,
yeah.
The mass. So this is you have in mind ordinary technicolor. Right?
Sorry.
In this, the mass of the rose will be the order of a tab. It's just a technicolor. The compositeness theory.
So
that is a sine theta somewhere.
Yeah, of course. Yes.
Large.
I'm being sloppy here about that.
Yeah.
So there is a factor.
Yes,
of
you try to treat the variation in mass of the Higgs proportional to the mass square of the rho times G squared standard model, like if you were a Goldstone Boson. But in an ordinary technicolor theory,
this
mass would be of the order tangent.
Yes, of course.
So it would be much smaller.
No, but I'm not talking about technicolor. I'm talking about composite Higgs.
So that would be then the 25 tab, not that tab.
You mean for...
So if you just take an ordinary strongly coupled theory,
yeah,
and you go in the limit, I mean, so once you have a strongly coupled theory, assuming there exists a four-dimensional strongly coupled theory of plastic, and that it can exist, then in general, if you have a Goldstone boson that looks like the Higgs, it will be also the technicolor spectrum by just changing the angles over which you...
Yes.
And if you get it closer to the region where you actually have a small angle,
yeah,
then you have to move. Then mass of the rho is divided by sine theta.
No, but here what I mean is really the mass of the rho that will enter in this. This
but that would be 25 theta.
It depends because for me it's a parameter. For me the mass
by sine squared theta.
No, but here the mass of the rho. This is the mass of the first resonance. Okay.
Yeah.
I didn't tell you how much it is. It can be 1 TeV. It could be like 10 to the 11 GeV. Okay, so it's just a parameter. So let's say I call the first resonance the rho in analogy with QCD, but I mean this has nothing to do. Okay, so this is just a parameter. Okay, so actually this will be made precise later. Okay, so you will see that really this formula is true as it is true in QCD. So okay, so this is the general idea of the composite Higgs, and So now, in general, if you have a strongly coupled theory, you're not guaranteed to get line scalars. However, there is a way where the scalars are automatic, and is when there is a dynamical symmetry breaking. So the idea of that I will describe is the idea of the composite Higgs, where the Higgs is actually a Goldstone boson of some dynamical break. So this is in general. So if you have a global symmetry G that spontaneously breaks to H at a scale F, that for me will be greater than electroweak band, you have a number of Goldstone bosons which is given by the difference of dimensions of G and H, and also the quantum numbers of this field they are entirely fixed by group theory. Okay, so you can open the Zlansky tables and see what you need. And so the idea is that the Higgs itself, so the full doublet, is an approximate Goldstone boson, and so this means that there is a global symmetry G that sometimes breaks to H, and here is the big difference from Technicolor, that the standard model can fit inside H. So this goes back to the work of Georgian and Kaplan in the 80s. So the most minimal, from some point of view, example is ISO5 broken to ISO4. It gives you...
Can I be a little bit provocative? Yeah. In which way this is different from technical, given that if you have a Goldstone boson,
so this is my definition.
You always have the technical limit too.
No, this is my definition. Okay, so in Technicolor, in Technicolor, there is no way that the standard model gauge symmetry can fit inside H. Okay.
Why not?
Because if you have SU2 cross SU2, we broken to SU2, and you gauge SU2 left.
I make this clear. If you have a four-dimensional gauge field for which you have a Goldstone limit, then there is always a technical limit too. So this theory is sufficient.
That's true, but that's different.
But that means you can never really disentangle the Higgs or from the technical.
Not entirely, because for example, if your global symmetry is SU2 cross SU2 broken to SU2, like in QCD, you will not be able to find a limit where you restore the symmetry.
I'm saying the opposite. If you claim that there is a Goldstone Higgs, then it will be always the technicolor Higgs. Vice versa is not true. So I'm saying that this is, if you want a theory where there is a Goldstone Higgs, then it will be always a technicolor too, but not vice versa.
I think this is just a question of semantics. Mine is just a group theory.
Well-defined field theory.
No, it's a question of semantics, because you can make a definition that englobes the more general categories of models, or not. This is just...
So take a QCD light theory. I mean, this is not
no,
really...
wait, just a sec. I think this composite Higgs label that you might not like is just the classes of model where the standard model as an unbroken symmetry is a good approximate symmetry of the...
Where the standard model doesn't break.
Yeah, yes.
Basically.
So there, if there is a limit where the standard...
embedding in a generic four-dimensional field theory, and that is a subset of a potential technicolor theory.
Exactly.
So it's not the different.
But you can still call it this way and define this as this subset.
Yeah, it's a subset if you want. Yeah.
It's a subset.
But this is not
so
a...
that's why it's
not
semantics.
different. The question, I'm actually projecting the word different. There's no difference. It depends on the way you embed it inside a global symmetry.
I think it's... okay, I think we understand what we mean. So... let me just go on. So, I mean, my definition is basically just a group theory definition. Okay, so if you want to think of it as the deformation of a technicolor, for me, it doesn't make really any difference. In fact, many features are similar. So, okay, so if you want to realize this paradigm, you have to find a symmetry breaking pattern that gives you a Higgs doublet. And so, simplest example, SO5 looking for SO4. There is many other possibilities, but some of them are described here. So this is just based on group theory effects. Now, the nice thing about the Higgs as a Goldstone bosons is that the deviation from the standard model, they're measured by this ratio of V squared over S squared. And so, where F is the dynamical symmetry breaking G to H. And so, in this theory, by taking F large, you have this parameter where that by this parameter, you automatically can get as close as you want to the standard model. So this is built in the theory. And however, of course, there is a price to pay, as in all things, because in this theory, the Higgs is an angle, so it's a quantity that can take values between 0 and 2 pi f. And so if you want to make the electric value much less than f, then you will have to pay a tuning, and this tuning scales in this theory have f squared over b squared. So typically, you are interested in natural theories. That's the main motivation of these type of scenarios. And so in this case, so you look for theories where, for example, v is less than f. Where f is less than tv, which corresponds to a relatively small tuning. So in this type of theories, you have the following spectrum. So you have you have the standard model degrees of freedom. Now there is also the Higgs, which is a pseudo Goldstone boson. And then you have the resonance of the theory, which are at a scale related to the scale f by coupling chiral, similarly to QCD. And so, because f is not very large in natural theories, this resonance will also be relatively light, and some of them might be accessible at LHC. So the other important ingredient that you need in this type of description is this concept of partial compositeness. So in this theory, the idea is you have the strong sector that delivers the Higgs, sometimes also the top, and then you have another sector which contains everything else, some model fermions and gauge fields. And the assumption of partial compositeness is that these two sectors they talk by linear couplings. So for gauge fields, this corresponds to a coupling of the fermionic gauge fields to currents of the strong sector. And for fermions, it corresponds to coupling of the standard model fermions to some states of the composite sector of equal quantum numbers. So the first step is standard. So in fact, it also happens in QCD. It goes under the name of photon row mixing. The second step is an assumption that is a restriction on the type of dynamics that you want to consider. So these linear couplings, for what concerns the fermions, they induce they induce a mixing, and once you diagonalize the mixing, you will generate the Yukawas. They have this specific structure of being proportional to the left and right mixing of the standard model chiralities. So this assumption is nice from logical point of view because it improves a lot the flavor, so the theory of flavor in this type of theories. So that's a motivation to require partial composites. So with these ingredients, so you will have that the Higgs, which starts out as a Goldstone boson, it becomes a pseudo Goldstone boson because these couplings they break explicitly the symmetries, and you will have a potential that is generated in one loop, and in some cases you can even compute it. So this whole business started in 5 dimensions, so with so-called random ensemble constructions, using the ingredients that I described in the first slides. And from 5-dimensional point of view, this idea of partial compositeness is quite natural because it corresponds basically to the localization of zero modes of fields in the x dimensions, and also the hierarchies they have a nice geometrical description in terms of localization, different localization across the x dimensions. So people have constructed explicit models. So I will not go through the details of this, but so this is, for example, a scheme that people have considered, and you can really get concrete models where you compute things. One thing that you can compute, so one thing I should say that these 5-dimensional theories, despite their 4-dimensional strongly coupled description, they are weakly coupled, and so they allow you to compute. So one thing that, for example, you can compute is the correlation of the Higgs mass with respect to the mass of the first resonances in these 5-dimensional models. And you find, for example, a correlation that tells you that the light Higgs calls for light resonances in this theory. So this was very much inspired by ADS-CFT, even though here we are in a regime very far from ADS-CFT. And in fact, so despite the fact that we use these weakly coupled computations, so it's fair to say that the 5-dimensional theory is not entirely weakly coupled. And the reason is related to the fact that this theory, they cannot live really at large n from a logical point of view. So let me explain you this. So this theory has, so the 5-dimensional theory is a non-renormalizable theory, which has a cutoff related to the gauge coupling. And so the number of effective degrees of freedom that you can trust within the effective theory is roughly of the order of the cutoff divided by the mass of the first resonance. And you have many observables, notably the S parameter, which will actually grow proportionally to the number of degrees of freedom of this theory, or the weakly coupled degrees of freedom. And so, to comply with experimental constraints, you somehow had to live not very far from strong coupling in the 5-dimensional regime. So, if you want to build a realistic theory of composite Higgs, at the end of the day, you cannot really ask for n to be very large. So let me just mention that very similar ideas have been employed for QCD. So from this point of view, is in the same universality class. It just changes the type of symmetries. So you can parameterize, for example, the Kalman symmetry breaking from an extra dimensions. So this is the simple example with implemented with boundary conditions. And so people have played with this, and you find actually quite nice agreements with experimental results in QCD, even though this is not entirely guaranteed by the symmetries of this theory. So So to move on, I would like to describe, to go back to the four-dimensional description of these Goldstone boson theories, and and there is various motivations for this. So some of them I already kind of explained. So from a theoretical point of view, practically there will be only in the theory of interest there will be only few resonances which are weakly coupled. Second, the relevant physics is largely independent of five-dimensional, or even less from ADS. And then there is the most important question: is that what are the most general models that you may find? There is also some practical interest that the LHC will at best be able to produce the lightest resonance, and so it's not worth to keep the full complexity of the external measure. And for this, you need a simplified model so that you might test at LHC.
Can I ask you a question?
Yeah, please.
So these 40 descriptions are, of course, useful in any case. But I mean, does one really learn anything then at the end of the day from the 5D picture? Since, as you said, I mean, you
yes. Thank you for asking, because this is precisely the point of this talk. I will show you some concrete examples where things are very far from 5 dimensions.
Yes.
Where you get like
but also basically what you're saying is that the 5D, anyway, you cannot use the weakly coupled 5D analogy because you can't really be a deep coupling, I mean, for phenomenological reasons.
Well, strictly speaking, I mean, you can debate, for example, if QCD NC is a lagrangian or not. Okay. 3 is a lagrangian or not.
Yeah.
Or
okay, sure. So, but, yes.
Strictly speaking, we don't even know if there's any dual or gauge dual. Which
yeah,
is
of course.
So technically speaking, unless it's supersymmetrical and maximum,
yeah,
this exponential construction might not at all be relevant.
No, it's true. It's true. It's just like, for example,
even if it would exist a lagrangian limit, there is no proof of that either.
That's absolutely true. It's just like, for example, I mean, this approach that could have failed, I think, 100%.
No, but it depends.
It didn't fail 100% here.
But it's also a question of what does it really mean in proving this picture. There is no small parameter which here I can actually control. Right?
But I could think of this a lagrangian. Okay, so I could think of this a large. So this, for example, in the weak coupling here, you can achieve. Think a QCD a lagrangian, and for example, comparing with lattice results in QCD.
So how would you possibly know before? If you did not have the result from QCD,
yeah,
which one will be 10%, which one will be 2%? This is completely no.
But there is some of these predictions, within this framework, some of the things that it will predict, they should become more sharp at lagrangian.
So, but I mean, there is not even a guarantee that the dual exists. So there is no reason that even if with infinite n, this theory is actually dual to QCD. So given that I don't even know there is this.
On the other hand, you may say, okay, this is a weakly coupled theory of mesons, and you may look for an effective description of that.
Let me rephrase. I didn't say it's not interesting. So I'm just saying you can definitely calculate, but there's no guarantee that you're describing any four-dimensional gauge theory at all.
Right. Yeah.
That's all
So,
I'm
in fact,
saying.
but yes. Okay, so let me move to four-dimensional description. So so there is a general way to describe. So I will be interested in spontaneous circular break, and there is a general way to describe a spontaneously broken global symmetry G2H, which is a bit technical. It's so it is called the CCWZ construction. So I will not really walk you through this. So there is is essentially a geometrical construction that allows you to buy the most general Lagrangian within an effective field description. And so this is very sharp actually for what concerns the Goldstone bosons, and things become a bit more model dependent when you talk about spin 1 resonances, which is really what you are interested in, because most of the Goldstone boson physics is constrained by the symmetries. So here we make the assumption that it seems to be true that spin 1 resonances can be described by gauge resonances, and I will introduce them in a slightly different way than usual, which is the following. So I will focus on particle symmetry breaking SON broken to SON minus 1 for simplicity, but it also accounts for the examples of composite Higgs and QCD that I will describe. So this has the advantage that you can parameterize this breaking with a vector of SO5 of SON that acquires a band. So with the constraint that the modulus of this field phi is equal to 1. And so this will give you the low energy Lagrangian to the limit which is model independent. And to introduce the resonances, what I will do, I will introduce a new Goldstone bosons, which are associated to the particle symmetry breaking SON cross SON broken to diagonal. So this gives the Goldstone bosons which are in the adjoint of OSON. And at this stage you have three global symmetries which are SON left, SON right, and SON here. And to introduce the resonances, what you can do, you can just gauge this diagonal combination of SON right and SON. So these two symmetries, you can gauge them. You can gauge the diagonal. And so this will introduce spin-1 resonances. And if you look at the physical degrees of freedom of the theory, you will have Goldstone bosons and massive spin-1 resonances, which have even the Goldstone bosons contained in this associated with this spontaneous symmetry breaking. So to note that in this way, it is really quite natural to introduce resonances which are in the unbroken and in the broken group. So this, if you think about QCD, will correspond to the rho and the A of QCD. So in this way, you get this Lagrangian, and you can go on. So you can add more and more sigma modulo to engage diagonal symmetries. And so you get this type of theories, of four-dimensional theories, which are described by this Lagrangian, which has the feature of having only nearest neighbor interactions. So not very surprising if you take the unit where you have a large number of resonances. This just recovers the five-dimensional theory. However, so it recovers the five-dimensional theory, and in fact, this is literally the discretization of the five-dimensional gauge theory. However, this is not the most generally effective field theory you can construct, and I will show you in a second what is the most general one at two derivative level. So I will not say much in this talk about fermions, even though they are very important, in particular for the composite Higgs, because they have a large contribution to the Higgs potential. But essentially, everything that I do for gauge fields can also be done for fermions. And just to let me give you an idea of how this works. So, for example, if you want to introduce fermions in one of these models, for the composite Higgs, you will introduce the Dirac fermions at each site that will communicate by means of these link fields with the fermions at the next site. So with these nearest neighbor interactions. So for what concerns fermions, in fact, there is some degree of freedom of how to use the site next to each other, the talk. And so one that is inspired by five-dimensional theory is that you have this type of left-right structure where the fermion site I, the less chirality, only couples to the fermion with chirality right at the next site. So this is just a technical choice you can do, and it's the discretization of the five-dimensional theory. Now let me go to the. So what I just described is not the most general description. It's something which is somewhat derived from five dimensions, and it's quite obvious how to construct the most general thing. So you have these link fields omega k, which connect the site k with the site k plus 1. And so you can construct, for example, this product, which omega ij, which connect the site I to the site j. So it's just the product of the link fields in the middle. So this you can draw like these link fields, and they are constructed in terms of the nearest neighbor links. And so with this you can write what is the most general Lagrangian, which I wrote here, so which contains all these link fields between site I and j. So in fact there is two terms. So this one is the term that contains mass terms for gauge fields, and you can also add non-nearest neighbor interactions for the kinetic terms that are wrote here. Of course, that will be of at a higher order than derivative expansion of it here. Okay, so this is just technicality. SO5 and SO4 is a bit special because SO4 is reducible, and so you write an extra term. So this has some relevance for phenomenology, but I will not talk about it here. And now you can actually show so this theory I built just based on the principle of gauge invariance, and you can connect to the CCWZ construction, which from this point of view is just a choice of gauge. So you can choose your gauge, for example, where the physical Goldstone bosons they all sit in the first sigma model. So you make this choice: omega 0, 1 equal to u, and the other equal to the identity. And so if you express it, then this gives you the most general CCWZ Lagrangian, and it's nice that in fact from this point of view you never have to talk about Maurer-Cartan forms and things like that. I mean, this is just it's just built in the gauge invariance of the theory. So there is many information that you will extract from this theory. So let me just derive the one that will be useful for my examples later on. So you can solve the equation of motion. You find that you have the resonances which are in the broken group are called ρ, and the resonances which are in the broken group which are called A, and one will be to be in order proportional to this quantity E mu from the Maurer-Cartan form, and this will be proportional to E mu with the coefficient which is just obtained from a linear set of equations. So with this you build, for example, the Goldstone Boson Lagrangian at a higher order, obtain integrating out these heavier resonances. So this is the exercise that has been done in many different years, but it's really always the same computation. So I mean, this is the result that you find, for example, for this set operators that you will generate at 3 level. And you see, in fact, that you find some rules between the coefficients of these operators. In fact, we found this in the example to do with the originally. And you also find that deviations from the sum rules they are parameterized by the non-minimal kinetic terms. So, for example, you see that here, you have C4 plus equal to minus 2C5 plus, which are the coefficients of these two operators. And this degeneracy is broken once you introduce the non-minimal kinetic terms. So, non-minimal kinetic terms are these ones. So, this will be important for the QCD application. The other tool that you need in many computations is the generating function of the currents of the theory for what concerns the bosons. So this has a form which is fixed by the global symmetries of the theory, so it is parameterized by two form factors which are pi 0 of p square and pi 1 of p square, which are related in this way to the 2-point function of the currents of the broken and unbroken group. Yeah?
Okay, so if I take literally Lagrangian QCD,
yeah.
There are, besides vectors, there are also other resonances, spin 2, spin 0.
Yeah.
In this approach, if I understand correctly, there are only spin 1.
Well, what I did only spin 1,
yes,
and I may do spin half.
No, I mean just in QCD, Lagrangian, there are,
yeah.
when you say that, for example, mapping in QCD, there's an infinite number of interacting resonances that are not only spin 1, they're also spin basically 0, spin 2, and so forth. So in this approach, they're not there.
I'm certainly not considering that.
We do know that even if I take the large infinite limit, this approach will never reproduce large QCD, because in large QCD will be actually an infinite number of other resonances which are not of spin 1.
Yes,
Which is
true. I could try to describe them. But
Sure, no, I'm sure.
it's true that it will face difficulties.
I'm just saying that
yes.
I cannot.
Even though, like, I mean, is it known the spectrum of QCD lagrangian? I mean, for example, what is the spacing between
What you
spin
can
2 and spin 1?
demonstrate is what are the leading N fields.
Mhm.
They're not all spin 1.
They are not.
Well, all, I mean, a lagrangian, the generic, you see, lagrangian QC is a qualitative thing, right?
Yeah.
But I mean, you can prove that there are an infinite number of colors and a fixed number of flavors. You have all kinds of spins as long as you close the loop with only a QQ bar outside and there is all blue inside. So that's all there is. And
But this tells you like a bound on the mask, for example, is spin 2. This just
But no, but they're all, I mean, there is all never lighter, I mean, if you take QCD or in QCD and you just look at the spectrum, the physical spectrum of QCD, you see in fact that after the first spin 1 resonance, there are spin 2, there is spin 0, they're all actually alternating each other. They all enter in the coefficients of this effective Lagrangian because you can no longer eliminate them if you add these other states. Right? So technically all that.
Yeah.
I mean, just like that is what you have many sectors that with different angular momentum level of B.
no, of course that there is all spin. So this is just for spin
It's
1.
just counting the QQ bar. I mean,
Yes.
after reading it.
Okay, so I'm going very slowly. So I'm describing this because it enters in what I have to say later. So these 4 factors you obtain in this apothier integrated out the resonances. So for example, pi 1 of q squared is what you of p squared is what you find. And this type of construction has it's very useful to realize the idea of partial compositeness. Okay? So it just amounts to introducing elementary kinetic terms for the elementary fields. So let me move to applications now. So let me describe SO5 to SO4. So you have so you can describe the simplest description is just corresponds to introducing one resonance. So this is the first construction that I presented. And so in this way, you will describe, in fact, SO4 resonances and the resonance in the cause of SO5 broken to SO4. And you can do the same for the fermions. So this is the Lagrangian that you will write down. So let me just say that the important point is that there is some composite physics which describe fermions with a global symmetry SO5 is potentially broken to SO4, and then you have some explicit breaking which corresponds to the coupling with some other fields, so which are the elementary fields. So in this theory, as I said, you can compute for example the potential for the Higgs because the Higgs is a Goldstone boson. It is born as a Goldstone boson, so it is massless. But once you introduce these explicit symmetry breaking parameters, you will generate a potential, and so this so the leading contribution is a one loop, is the economic effective potential. And this theory is so you have very simple formulas compared, for example, to the 5-dimensional causings of these type of theories. So this correlation that you find, so you find a correlation between mass of the fermions and mass of the Higgs is, as you see, is quite similar to the one that you had in 5 dimensions without the full complexity of the 5 dimensions. So let me now discuss a bit more in detail this connection of the masses of the resonances and the Higgs mass, so the Higgs potential. So in the thing that I just described, the potential is finite, and the finiteness of the potential depends on this integral for what concerns the gauge loops, which is pi 1 of q squared divided by pi 0 of q squared. Now, in a model-independent way, you have that pi 0 q squared grows like q squared at a large momentum, and so finiteness of the potential. It corresponds, is translated in the so-called Weinberg-Sum rules. The first one that eliminates the quadratic divergence, so is the requirement that pi 1 of q squared goes to 0 faster than the one with q squared. And the second Weinberg-Sum rule eliminates also the log divergence, and so it corresponds to this constraint. Now, in the most general description, you have that pi1 of q squared is some function of q squared divided by the product of the q squared plus the mass of the resonances. And what happens if you have the nearest neighbor interaction? So you have that the numerator is in fact independent of q squared. So this has a convergence which is 1 over q squared to twice the number of sides. So in fact you can understand this diagrammatically very easily. So this pi1 of q squared has to do with the symmetry breaking in the theory. So you need to communicate from the sources of the effective description to the symmetry breaking. And to do this, you have to go to the resonances, and every time that you encounter a resonance, this corresponds to 1 over q squared in pi1 of q squared. So the living behavior is that pi1 of q squared goes like 1 over q squared to a distance that you can define, and this distance is just the number of resonances that you encounter for the path that goes from the source to the symmetry breaking and comes back. So this is the number of resonances. So this is the distance. So from this point of view, the extra-dimensional theories are theories where the distance between the elementary fields and the symmetry breaking is infinite. So if you take these nominal terms, what these nominal terms do, they actually shorten the distance of the path. So that, for example, this theory with the k sides will have a pi1 of q squared, which is reduced. It just goes like 1 over q squared to the 2i. Or this is another example. So what matters is always like the shortest path that you can draw along the diagram. And so this is the equivalent, geometrical equivalent of the Weinberg sum rules. Okay, so the Weinberg sum rules, from this point of view, they just correspond to the locality in this modes. So this is a very intuitive way to understand this convergence. So this also tells you that once you go beyond the nearest neighbor interactions, it will not be necessarily the lightest resonance that will cut off the potential of the Goldstone bosons, as it happens in the example that I showed before. So you can have like the connection really between the lightest resonances and the finiteness of the potential. It's removed in this theory. So this is an important result. So I think I don't have much time to describe also the fermions, but let me say you can also play the same games with fermions. So here is actually more fun because you have left and right chirality, so you can define different paths for example, correlator will left and right chirality, and the left and right. And this has implication for the potential that depends on this type of correlators. So, but the conclusion is what I just drew before, is that the potential is in general not saturated by the lightest resonances in this theory, contrary to what happens in extra-dimensional theories or the avatars with the nearest neighboring interactions. Other interesting thing that people consider is S parameter. So, it can be defined as the coefficient of this effective operator. And so, if you have resonances, you can have 3-level contribution to the S parameter that will scale like 4 pi d squared divided by the mass of the resonance. Now, in this theory, you can really derive a very simple formula, which has to do with the which is possible because the Higgs is a Goldstone boson. So the 3-level contribution is just related to the pi1 form factor in the theory, and it has two terms. One that depends only on the masses of the theory, and it is positive definite, and another one which depends on the numerator. So it's not positive. It's not positive definite in particular. So for nearest neighbor interaction, you have that the numerator was constant, so this implies that delta S is always greater than this minimum value. Okay? And this was a result that in fact it was originally found in 5 dimensions. And in fact it's very simple, it just depends on the spectrum of the theory. So if you move to non-nearest neighbor interactions, you can get all kinds of values for S parameter. So if you introduce this link that connects sources to symmetry breaking, so then the result is just multiplied by this quantity that can be even 0 or negative in principle. However, this example is perhaps not the most compelling, because in this case you will have that the potential for the Higgs that you get from gauge loops will be quadratically divergent. So because you are connected, so because essentially the distance between the elementary fields and the symmetry breaking is 0. However, it is still possible if you complicate a little, if you add an extra degree of freedom, as I did in this case. So I introduce yet another set of resonances. So this is a two-side model. In fact, I'm taking also the limit where this F23 goes to infinity, which corresponds to eliminating one coset resonance. And so this is the formula that you find for the S parameter. This in particular when this link F02 is different from 0. And so these are plots in the general case that shows you that you can go actually below the nearest neighbor, the minimum nearest neighbor value, which is given by this curve. And in principle can even be 0 or negative. So this is a very different result from what you will find in the next dimensions. So let me, how much time do I have? 10 minutes, very good. Okay.
No, 5.
Okay, I think, yeah, 5-10 minutes will be okay. So let me now apply this to hadrons. So it's kind of fun. So let me consider a simplified version of QCD where you have just two flavors. So the pattern of symmetry breaking is SU2 cross SU2 broken to SU2. And this, for my purpose, is the same as SO4 broken to SO3. And so you can introduce, as I did before, vector and axial resonances by considering SO4 gauge theories. And so this is the nearest neighbor moves that you will consider. And so this is a fact from a table from the paper we wrote with Diego, and which showed that already with these three resonances you find some kind of reasonable agreement with QCD data for many observables, as you see here. So there are some things that work, but there is also some things that they don't work so well. And what I will show you is that here is a place where these nominal terms might be relevant. So let me tell you about the pion mass. So the pion mass originates in this theory. So the splitting between so in QCD you have that the difference between the mass of pi plus and pi 0 is measured to be this value. And it is believed that the splitting between pi plus and pi 0 it can be explained by the electromagnetic splitting by the electromagnetic interactions that explicitly break the symmetry that relates pi plus and pi 0. Even though there is also some effects due to quark masses. So in fact already in the old days, people showed that this formula, so there is this contribution to the splitting of pi plus and pi 0, which is expressed in terms of this form factor pi 1 of the effective Lagrangian that I described before. Now for SO4 goes into SO2. So if you really want to compute it, you have to consider a model. And the simplest model where you can compute is the one where you introduce the rho and the A1, and then you find this explicit formula for the electromagnetic split in the pions, which agrees quite well, I think over 20% with this splitting of pi plus and pi 0. So this is nice, but it doesn't fit well with other features. So in QCD, this ratio. So if you consider this ratio in this theory, it's fixed, has this value 3.4, and in QCD, this ratio is very close to 2. This is known as the second KSRF relation. And in fact, it is really very close to 2 that people want is this an important feature of strong coupling. Now, if you describe theories, so this is in order one failure of this description that we want resonances, but more in general, even if you introduce nearest neighbor interactions, you can always prove that this is always greater than 3. So you can always you can never get close to 2. So this is a place where nominal interactions become relevant. So, for example, so you can consider it still the version with of the theory with just the rho and the A1, and if you introduce these nominal interactions here, then you have an extra parameter which is F02 that allows you to fit this result, the experimental value for this quantity here. However, if you introduce this non-minimum interaction, you have that the splitting of pi plus and pi 0 is not anymore factorable, and so it becomes polarity divergent. And so, for example, you might expect that it would be cut off at the next resonance in the theory, and but if you do so, then you spoil the agreement with the electromagnetic splitting of pions that you measure. So the two things can be put together if you introduce the rho prime, which is the next spin-1 resonance in QCD, and introduce non-minimal interactions. So in this case, you can have at the same time a calculable potential and reproduce the KSRF relation. The other interesting thing, the other place where nominal interactions can be interesting is this relation that you have between L9 and L10 in QCD. So this is the chiral lagrangian QCD to 4 derivatives, and you can compute with the tools that I described earlier. You can compute the coefficients of these higher dimensional operators in obtain integrating out the resonances in my theory before. And as I said, you get some rules that relate some of these coefficients, and in particular you have this you have a relation between at 3 level you find that L9 is equal to minus L10, which is verified at order 10% in QCD. On the other hand, this relation can be spoiled if you have non-minimal kinetic terms. So this is interesting because these non-minimal kinetic terms basically they take away from treating the resonances as gauge resonances. So in a sense, QCD is suggesting that so QCD data suggests that the right treatment of the spin-1 resonances as gauge resonances rather than other ways to describe them. And so this, in fact, I think is something would be interesting. For example, to know what is this ratio at lagrangian, whether, for example, like it becomes smaller as you would predict from extra-dimensional theories, or also from here. So this takes me to the end. So motivation for this work was that there is actually most physical systems that we are interested in these days. They require the understanding of the most difficult theoretical regime, which is strong coupling and small n dynamics. So the most general dynamics that you can describe in effective field theories is very different from X-dimensional and derived constructions, and this can be done in two ways: blindly using the CCWZ construction, or with nominal terms that are described that essentially allow us to control the deviations from geometries. So this so I showed some examples where this might be relevant, in particular composite models and QCD. And so you find very different results from X dimensions for what concerns S parameters, Gaussian resonances, Higgs mass, and pion physics. And so it would be interesting to check these nominal terms with other theories that, for example, people may consider on the lattice. So I'll stop it here. Thank you.
I'm not sure I probably said it and they missed it. But do you have a prediction in the end for a mass of a resonance? Were you able to make a prediction?
In the Higgs,
For example, what is the next resonance that it sees?
it's well, no, you don't have a prediction. It depends on the amount of tuning that on the amount of tuning that you allow yourself. So the resonances can be arbitrarily heavy in principle.
But you have.
So if you require a natural theory, okay, then there should be some resonances which are light.
Which are light.
So what I showed is even worse than this. Okay, what I showed is that like even if you have light resonances, this will not guarantee that the theory is natural. Okay, but if the theory is natural, you definitely have to have resonances.
And how light would they be?
So here, okay, so if you do these extra-dimensional models or these four-dimensional avatars, so you find the correlation that the Higgs mass 125 tells you. So this is for F. Everything is controlled by this parameter F.
So around
So-
the TV.
So this around TV, yes. So
Between alpha TV and the TV.
yeah. So this is basically consistent with naturalness. What you know just from cancellation of the quadratic divergences. So here you really see it concretely because you can compute this quantity within certain model, but you can compute. Okay, but it completely agrees with the naive tuning that you would obtain with the cutoff, for example.
Is there no way that one could also get these non-minimal terms from extra time? I mean, okay, so to me this is a nice counting scheme because at the end of the day I think basically the conclusion is that the extra dimensions don't really teach you anything because it's not really applicable and it's not general. The things people have written down as opposed to this. Which, okay, so then you can write down the effective lagrangian in very different ways. This is a nice one because you have a counting scheme, or not counting scheme, organization scheme. But couldn't one have gotten these non-minimal terms by adding terms in the bulk in extra dimensions?
No, I mean
The most important thing is that how controllable are these non-minimal terms?
how controllable?
Yeah, I mean, you start adding.
Of course,
terms.
if you start adding higher dimensional operators, you can get whatever you want. But for example, you may ask, well, could I get these non-minimal terms, the most general non-minimal terms, just by integrating out the heavier resonances in the X dimension? And the answer is no, okay? Because for example,
does that not depend on what interaction?
so for example, like in X dimension, no matter how many you put, you always find this relation, okay, greater than 3. But if you put non-minimal terms, you find that you can get, for example, 2.
You need to allow non-locality of 5D.
No, but even, yeah, of course, if I did this would look like some weird non-local object.
Yeah, okay. So imposing locality in a 5-dimensional world, you kind of get over here.
Yes.
Yeah.
Certainly, but even if you, I mean, you do, so if you start from X dimension, okay, and you integrate out the resonances, you will generate non-minimal terms. Okay, but you will not generate the most general, the most general value for them. So, for example, in this deconstructed picture, suppose you have 2 resonances. So one is a heavier. Then you can write the effective theory, obtain integrating out this heavy resonance, and this will include some non-minimal terms for the lighter one.
Yeah.
But this is not the most general situation on the other hand.
Yeah, okay, sure. But then if I have something else I integrate out, presumably I can work backwards if I wanted to. I can just, well, okay,
I mean,
it becomes, there's not much point, because anyway, I guess it's nicer to work in the 4D picture like this. see. Can I ask another question?
Yeah.
So for example, this example with where you have a, you can even have a negative S parameter. So connection and the Raphael also found there. I mean, that just follows from the Weinberg-Song rules, right? That if you have 3 resonances, 2 vectorial and 1 axial, then indeed you can get a negative S and satisfy all Weinberg-Song rules.
Okay, I didn't know it in that language, but okay.
Yeah, so
this is what I find.
yeah, okay, yeah, and indeed that's also what they found. But I was wondering, how do I see it? Because you also mentioned that in that case, then you don't have a the Higgs potential is not.
No, okay. So there is 2 ways. So if there is a trivial way, to get an S parameter, for example, 0, by introducing this nominal term between the sources and the symmetry breaking.
Yes.
Okay. This is a term that does not talk to resonances directly. So then the formula that you get is this. Okay? And in particular, if you take f0k equal to f squared, then you get the S parameter 0. On the other hand, what happens in this limit is that the Goldstone bosons they decouple from the resonances. So you don't have anymore a trilinear vertex. So, for example, they do not contribute to unitization of scattering of Goldstone bosons.
Yeah.
Or so basically is I mean the resonances they don't play a role in the physics of the Goldstone bosons. On the other hand, so if you consider like this other situation, you can where you don't put like the connection between the sources and the symmetry breaking, you can still have that the resonances play a role, and however the S parameter is suppressed, or in some cases here even negative.
Yes.
But so to be fair, I mean, one should consider, we haven't done so, what is the role of the resonance in this type of theory. Okay? For example, the question of unitization of scattering of Goldstone bosons in this theory.
But I thought in that second example you said explicitly that you could see that there the Higgs potential is not.
No, here the Higgs potential is calculable. Okay? But there is 2 things. One is the Higgs potential, which just depends on an integral of the form factor, and the other is the 3-level scattering of the Goldstone boson that grows with energy, and so at some point you lose you exit the validity of your effective theory.
Yeah. But I think so. This is yeah.
So there are 2 different questions. For what concerns the calculability of the potential, what matters is just basically this distance.
Yes.
So this move is shorter than this one, because here the distance between sources and symmetry breaking is 0, and here is at least 1.
Any other questions, comments? No, that, thank you.